that 2 point charges minus 4 microcoulombs and 5 microcoulombs are located at this point and at this point, respectively. So the potential at this point is obtained as we're going to use the superposition theorem to add the two of them, and we are saying that is going to be given by due to the first charge and due to the second charge plus a constant. This is going to be 0. That is what the 0 potential at infinity says. And therefore, R minus R1 is simply given by the observation point is this one. So we are saying 1, 1, 0, 1. Sometimes I like writing them like that. And we are doing the magnitude of this. So then the source point is B. So we are going to have 2 minus 1, 3. And when you get the magnitude of that, you have 1 minus 2 is equals to, you normally get the square root, which is 1 minus 2 becomes minus 1 squared, plus 0 minus minus 1 becomes 1 squared, and then 3 minus 3, 1 minus 3 becomes equals to 2 squared. So this is equivalent to root of 6. So the root of 6 is the one that we obtained right there. And therefore, when you now replace this with root of 6, and we know the epsilon naught can be expressed as 10 power minus 6 minus 9 over 36 pi. And therefore, you just replace that. And we can also see that Q1 is equals to minus 4. And you are putting the negative or 10 to the power minus 6 outside as a common factor. And so that works for the first case. And for the second case, you do the same, except that we are now saying R minus R2 modulus, and we know R to be 1, 0, 1. Then you minus R2, which is this one, which becomes 0, 4 minus 2. And when you do the modulus of that, what that will give us is simply 0, 1 minus 0 becomes 1 squared, plus 0 minus 4 becomes 4 squared, plus 1 minus 2 becomes 3 squared. That becomes root of 26. And that root of 26 is this one. So when you now take your 5, which was the 5 microcoulombs, and you now put that in that formula, and you solve, you actually get this place to be minus 5.872 kilovolts. This is kilovolts, or rather volts times 10 power minus power 3. So, well, that example is rather straightforward. The only point we are saying is that we take this to be equivalent to V. This would be equivalent to VR1 to R. And therefore, we are saying that this is the point of observation, and this is the point, this is the source. So the same idea, I think, if you were to express it, this point to be A, this point to be B, and this point to be C, then what you would end up with is this would be equivalent to VBA. Yeah, I think that is the bit that was a bit confusing, and plus VCA. So this is the source due to C, and this is due to B, and the B have given them this point and this point, and therefore when you add them, they give you VR1 and VR, and when you solve that, it gives you this solution like there. When you do that problem, you actually find it rather straightforward, particularly when you understand what you're talking about. Continue. So here's an example 411. You look at that on your own. I think we'll just jump to the next section that is important. We plan to cover, which is the relationship between E and V, which is actually gives us the Maxwell's equation. And before we actually proceed, I stated the Maxwell's equation here. You don't need to remember this one offhand for now, but we are saying that these are the 4 Maxwell's equations. And one of them is divergence of D gives us rho V, which we'll see later. Divergence of B for electrostatics gives us 0. The curl of E gives us 0. And the curl of H gives us J. J is the current density. So the one we are going to be dealing with right now is this equation right here. And we are going to see how we can actually derive it. But before we go there, we are just going to see how we develop that relationship. So as shown in the pre-predicting section, the potential difference between point A and B is independent of the path taken. And we are saying we can always say that if you have VBA is equal to the negative of VAB, that is something we have said, that if you have potential, if you have if this is your point, your source, and you want to find potential at point P, which is this is point A and point B, then potential at this point, then you're calling the VAB, is going to be different if you replaced now, if you placed, if you looked for VBA, which would be the potential at point A, and you place this one at that point. And therefore, you are saying that it would become negative VAB, as you can see in equation, as in this equation. So, so what you're saying is that if you find the potential, of course, if you now add these two, if you add them, you are actually going to find that one is positive, the other one is negative, and when you add them, they give you the answer to be 0, because it is it is like we are looking for the potential, which is obtained by finding the cross-line integral of E dotted with L. So like, if you remember the very first diagram we were looking at, which was, I guess, somewhere here, let me show you that diagram. Yeah, in this diagram, if I rub this, and now you say that you won't find the potential, you won't find potential from point A, and this is point B. You go through across this path, that is path AB, and then you go from B to A, then there will be no work done. There will be no work done. Just a minute. Sorry for that. Therefore, so as you can say that there is no work done, because if you move this point charge from this point and then move it back through another path that is taking you from the origin, then you actually realize that you have not done any work, and therefore the potential that you had gained some positive potential when you are going through the positive through AB, and then you gain negative potential as you moved from B to A, and therefore when you add the two of them, then you actually realize that you have zero work done, and therefore that is what that equation at that point is saying. So the example I've recited is the one that crossed path line integral. So it is cross path line integral is the one that is giving us a zero zero integral, because one was positive, the other one was negative. When you add them or when you integrate them, it simply gives you a zero. Now, from this point, we are actually observing something that is really important. That we can apply Stokes' theorem at this point. We can apply Stokes' theorem in this equation. If you remember what we said about Stokes' theorem, now we apply Stokes' theorem on equation 473. It's something that it gives you. That you say that this cross-line integral will become a surface integral, where we are now introducing the car of E, and of course, instead of having the dl, now it will be on the integral with over the surface. So when you do that, there is something that we are still retaining with our zero on the right part of the equation, and therefore we can simply say that from this equation 47, the only term that cannot be zero, of course, the only term that can be zero is that we know E is not equal to zero, and a surface is not equal to zero. This is not equal to zero. Surface is not equal to zero. Therefore, the only term that can be zero is this term. And therefore, it is that term that we actually make a conclusion that car of E must be the one that is giving us zero. And that is a very important observation that now allows us to make some progress. And because we have observed that car of E must be equals to zero, then it is from that point that we say that from the quote I had tried to describe earlier, is that it must be conservative. And I said that any vector whose car is equal to zero, we normally say that this vector is conservative. And it is from that idea that we are saying that conservative. We're saying that that vector, because now our A is equals to this E, is becoming, we are saying that it is conservative or rotational. That means it has no component that is rotating. Because that is what we say, that if you have a vector that is displaying such a behavior, that this vector or the car of this vector, if this is my A, the car of this vector will not be equal to zero. But since we have seen that A or that E never has this kind of behavior, that it is always diverging outward. If this is my E, it can only be diverging outward. And if you try to evaluate its rotation component, you find it is equal to zero. That is what we say that the field E or the vector E is rotational or conservative. It is saying that, in other words, a vector whose line integral does not depend on the path taken or the path of integration is always considered to be a conservative vector field. So there is some further derivation that you're saying that equation equation 473 and 474 actually are the equations that we refer to as the Maxwell's equation. So if you look at equation 4, if you look at equation 473 and 474, the one I'm clearing now, these equations are the one that we are the one that make up the third, not second actually. It depends. Okay, these equations do not have numbers, so sometimes people take capital numbers to express them. But just notice that this is one of the equations that that were stated by the Maxwell, and one of them says that curl of E is equals to 0. So when I mentioned about curl equation, I was mentioning this equation. but it is stated in the differential form. It can also be stated in the integral form that is expressed as in equation 473. And therefore, that just states, we are not even going to be deriving or stating the Maxwell's equations. All we are saying is that this is one of the Maxwell's equations. So from that point, there's some further points that we want to state in regard to the scalar potential. And of course, what I was saying there is that 473 is the integral form and 474 is the differential form of Maxwell's equation. And both depict the conservative nature of an electrostatic field. Now, from the way you have defined the potential, this to be equals to this, or V is equals to minus integral of E dot dl, it follows that you can do some further analysis on using the multivariate calculus. And what you actually observe is that, anyway, there's something that we said it is rotational. And some factors that you said about E being rotational is that we said that curl of gradient of any vector of any scalar, say k, is always equal to 0. This is something we said when we are doing vectors, and therefore we are simply saying that since we have said that curl of E is equal to 0, then we can introduce and say that E must be gradient of a scalar k, and that scalar k is the one that you're actually saying at this point, that k must be equal to V, and that must be the scalar, electric scalar potential that we define. So look at this statement that we are saying here after equation 476, that the electric field intensity is a gradient of V. The negative sign shows that the direction of E is opposite to the direction of in which V increases. Or what we have simply said is that from this equation that I have stated earlier, is that we know that I've not drawn it properly. This is one of the statement that we said very long time ago. If V is a scalar, then gradient of V will be a vector. But then we know that if you have gradient, or rather curl of gradient of a scalar, will always gives you a 0. Therefore, what we are saying is that we are depicting that this, therefore, because we have seen that curl of E is equals to 0, therefore we are saying that this being the case, if you just consider this to be equivalent to this, then you're saying that this must be equal to that. And you're saying that E must be gradient of V. And then you're introducing this negative sign because the direction of E points in the direction of decreasing V. I hope that point is a bit clear. That if you have, I normally like to draw sometimes in my time to my drawing. If you, this is my Q, it is producing E, and you want to observe V1 at point 1 and V2. So the potential at point 2, V2 is definitely less than V1. But you're saying that E is directed towards this direction. So what that means is that E is simply the gradient. We have said it is a gradient of V, but since V is decreasing in this direction, then you can, that is why you introduce the negative sign at that point. So E must be the gradient of a scalar function. That is how we have come up this derivation that I was bringing this idea here. So probably you can look at it at some other time, but that is all that question 476 says. And we are saying something else that question 476 says that it shows another way to obtain E if you are given V. So if you know V, you can be able to obtain E, because we have now seen there are three ways in which you can obtain E. You can obtain E from the Coulomb's law. You can obtain E from Gauss' law. And now what we have done is that you can also obtain E if you are given V. So that is what we are trying to say at this point, that that is another way in which you can obtain E if you are given a V, because it has been defined by equation 476. So that takes us to the example 412, which I hope to do very quickly before time runs out. And you're told that given potential V is equals to this 10 over R squared sine theta sine cos phi, find the electric flux density D at this point. What we just know for sure is that I've opted to do it quite quickly here. That we know for sure that there's where we stated that curl of E is equal to 0. That is a statement. This is Maxwell's equation. This is Maxwell's equation. And we also stated somewhere that the electric flux density D is equals to epsilon naught E. I can write it here again. D is equals to epsilon naught E. This is something we also stated in our earlier lecture. If you know these 2 points, then you can say that, and you have said this should be the case. If you introduce epsilon here, before we even do that. But E, we know E from equation 4, I think 476, we have said is equals to negative gradient of V, and therefore means that we can introduce our epsilon naught there and say that this is equals to D. So now we have defined D in a new way, which is the one I'm doing at this point. That D is equals to epsilon naught E, which is equal to negative gradient of V. And here I have my epsilon naught reintroduced again. So I think there is nothing new in that statement, except that we have expressed D in a new way. Therefore, we can be able to look for the gradient of V since we are given this V here, because we want to find D. So once we have been able to do that, we'll just introduce the negative at that point, and we'll be able to find the total D. So look at this. We know that the gradient of V from our definitions that we did earlier is equals to this. See that this is in spherical coordinates. That is DDR VAR 1 over R DD theta VA theta 1 over R sine theta DD phi VA phi. So this is the definition of the gradient of phi. So you can start working on them. You can start working with this term, then this term, and then this term. When you work with the first term, you actually find that this is the one I worked on here. See that you are differentiating with respect to R only. So if you are differentiating with respect to R, and you know my V is this one, you can just take sine theta before it is not a factor of R, put it outside the partial differential. cos pi, put it outside the differential. And then what you're going to be left with is only one term, that is a factor of r, which is 10 over r squared. And then you still keep your unit vector ar there. So when you differentiate this term, it simply becomes minus 2 sine theta cos phi 10 over r cubed ar. That is the typical differentiations that we can do. And the other term that we are going to be working on is this one over r d theta v a theta, and you put it at this point. And since we know that r is not factor of theta, you put it outside the differential, and cos phi you put it outside the differential, and as well as 10 over r squared. So the only term that we are going to be differentiating is cos sine theta. So if I was to differentiate this with respect to theta, it would simply say that sine theta is the one that would become cos theta. Everything else remains the same. So that is what we have done, and we are ending up with cos theta coming there, and everything else remaining as it was before. And of course, your a theta cap, that being the unit vector. So the last term, which is this one, that you want to do the integration. And again, with the only factor that you're going to be differentiating is when you differentiate that term, it is simply going to become, you're only going to be differentiating this term, becomes negative sine of phi, and everything else remains the same. So what you are simply having is that you still have your 10 other things you have, but you're introducing this term here, and then you have your, and of course sine theta cancels sine theta that was there. You are left with negative sine phi, which is the one I've obtained here, and therefore you have my negative sine phi. My negative comes there. I had sine theta there, and of course I had sine theta here. This cancelled, so we end up with this term. So if you now introduce your negative in this equation that we had here, negative gradient of v epsilon naught, negative, and I introduce negative here, and I just introduce my negative, negative gradient there, then this becomes my answer. So what we end up having is that this becomes my E, but then my D is where the one I'm introducing the epsilon naught, and therefore, as you can see, what we have here is the same thing that we have obtained at this point. You can see this term is equals to this term. This term is equals to this term, and of course, this other term is equals to this term. So I guess you will see that when you're doing your revision, and you see that it comes in as clearly as that. So we are told you want to find the potential at this point. So you just replace theta r with 2. You replace your theta with pi over 2, and you replace pi with 0. So what that gives you is that if you just introduce your, let's start here. If you, this theta is pi, so you know sine of pi is 1. If you introduce cos of 0, this is 1, but cos of 90 is 0, and therefore the whole of that term goes as sine of 0 goes. So you will see that this goes to 0, this goes to 0, and you're only left with this term, which is 20 over 8. R is 2, so becomes 2 squared, 2 power cubed, 2 to power cubed becomes 8. So you can see this becomes 8. So this is the only term that remains. The other terms goes to 0. So we are saying that your D, you multiply with the epsilon naught, and you end up with the answer that we have obtained here. So of course I can see the time is running out. I think I will leave that to you to go through.